Hyung-Chan and Ulla Svensson. So before we start, perhaps it would be a good idea for me to review the definition of the problem. And for those of you who already know the definition, this probably is a good chance for us to make sure that we are using the same notation. So in a capacitated facility location problem, we are given a metric cost on a set of nodes, some of which are called clients and others called facilities. And the clients in this picture are represented as circles, and facilities are represented as squares. And of course, given that this is a metric cost, we have the triangle inequality, so the distance that connects two nodes directly is always no worse than a detour. In addition to this metric cost, we are also given as part of the input the capacity of each facility, denoted as U sub I, and the opening cost denoted as O sub I. And this facility, for example, has capacity 3 and opening cost of 20. Now the goal of the problem is to choose a subset of facilities that we say to open. And then the second goal is to assign every client to one of these open facilities. And while we are doing this assignment, we also want to make sure that the capacity constraints are satisfied. In other words, if we see any open facility, then the number of clients that are assigned to this facility cannot exceed its capacity. So this particular solution that I have shown in this picture is feasible. And among these feasible solutions, we want to find the solution that minimizes the solution cost, which is defined as the sum of the opening cost of the facilities that we chose to open and the connection cost from every client to its assigned facility. The uncapacitated facility location problem is a special case of this problem, where you assume that once you open any facility, then it can serve unbounded number of clients. And this, in fact, is a very successful special case of this problem in the sense that we have a nearly tight understanding on its approximability. So we have a 1.488 approximation algorithm for this problem. On the other hand, we already know that it is NP hard to approximate this problem by a factor that is better than 1.463. And this success was enabled by techniques that are based on linear programming relaxations, in the sense that, well, this best approximation algorithm for the problem, 1.488, was obtained by combining different LP rounding, different LP-based approaches. And in fact, several number of LP-based approaches, such as LP rounding or dependent rounding, randomized rounding, primal dual methods, dual fitting, and so on, they have all evolved from the research of this problem. And well, this algorithm was obtained by combining all of these techniques. So given such a huge success on the special case, the natural question to ask would be whether we can do the same thing for the general problem as well. If we can obtain an LP-based approximation algorithm for the capacitated facility location problem. And this question is particularly interesting because previously all of the known approximation algorithms were based on a single algorithmic technique, namely local search. So even though we already have a 5 approximation algorithm, it was still the question whether we can obtain a different method of approximation algorithm. Now, as I have mentioned, one of the reasons why we are seeking for an LP-based algorithm for the problem is because we want to access this rich toolkit of algorithmic methodologies that have already proven to be very successful for the special case of the uncapacitated version. But in addition to that, there are a couple of other practical benefits of LP-based methodologies. So one of them is that, well, when an algorithm is based on a linear programming relaxation, then once the algorithm computes the final solution, it also, as a side product, produces an LP solution, which is a lower bound on the true optimum. Therefore, for the particular given instance, we can produce a per-instance performance guarantee because we can compare the algorithm's output to the particular LP solution that the algorithm has found. And this per-instance performance guarantee is often much better than the theoretical guarantee that we can get from the analysis alone, and that can have some practical consequences. And also another reason is because often we can use similar LP relaxations for similar problems, so we can often hope that once you have a new technique in one of these problems, we can lift that technique and apply to other problems as well. And for that reason, this question, whether we can obtain an LP-based approximation algorithm for the capacitated facility location problem, was selected as one of the 10 open problems selected in the textbook by Williamson and Schmois. So the question is, well, why is this problem hard, or what's the difficulty? And at least in part, the difficulty comes from the fact that there is a standard LP relaxation that we use for facility location problems, but this standard LP relaxation fails to give any reasonable bound on the optimal solution value for the general problem. So, in fact, this standard LP relaxation was used for many of the relaxed problems, such as the uncapacitated problem that I have just talked about, or the version where capacities are allowed to be violated but by some provable factor, or some of the versions we allow facilities to be opened multiple times by paying more opening cost, and in some of the other problems opening costs are assumed to be uniform. So for many of these problems, standard LP relaxation actually gives a good bound and gives a good algorithm, but for the problem that we want to solve, it doesn't give any reasonable bound. So that was the difficulty. So in some sense, the challenge of this, the first challenge that we will face to answer this open question is that no LP relaxation was previously known that is algorithmically amenable. So what do I mean by algorithmically amenable? So in fact, given any, well, in particular, given any NP optimization problem, it is of course possible to come up with an exact LP formulation, because we can enumerate all the feasible solutions and think about this convex combination, and of course we can algorithmically write down all the facets. So even though that is automatically possible, but that will not necessarily have the necessary structure that we can make algorithmic use of. Therefore, the challenge is often to write an LP relaxation that is somehow still strong enough, but has a nice structure that we can make use of. So the main theorem that we are going to see today is that there actually is such a good LP. So I'm going to show an LP whose optimal solution value is within a constant factor of the true optimum. And the proof is going to be algorithmic, so I'm actually going to show on the way on the first LP-based constant factor approximation algorithm for this problem. So before I do that, perhaps I will need to introduce the standard LP relaxation, but which is slightly written in a different way compared to the usual way how we write the LP relaxation for the facility location problems. So if you haven't seen the standard LP for this problem, then don't worry, because I'm not going to assume any prior knowledge. So as was the case, well, both the standard LP relaxation and our relaxation are based on the same set of what is called decision variables. So these variables will encode the decisions that the optimization problem has to make. So for each facility, we define a variable y sub I, which denotes whether the facility is going to be opened or not. So the value of 1 denotes that the facility is going to be chosen as one of the open facilities. If it's 0, then it's not chosen. And then for each pair of facility and a client, we define what is called an opening variable, or sometimes an assignment variable, x sub ij, which again takes a value of 1 if the client j is going to be assigned to facility I and 0 otherwise. Now we are going to consider a multi-commodity flow network where the set of vertices are given as the set of clients and the set of facilities. So this is a multi-commodity flow network where we define an arc from a client to a facility whose capacity is exactly equal to the decision variable that we have just defined. And then we declare that every client becomes a source of its own commodity with demand 1. And each facility is going to be a sink whose capacity is given by the capacity of the facility But this capacity is going to be shared by all the commodities. So I'm going to call it commodity oblivious capacity. But in addition to this capacity, it also has a capacity that only applies to each specific commodity, whose capacity will be given by the opening variable times 1. And then we can see that, well, this multi-commodity flow network, which actually corresponds to a feasible solution where we open these 2 facilities and assign these 3 clients to here and these 3 clients to there, the multi-commodity flow network we have just defined using that feasible solution does have a feasible multi-commodity flow. And then we can also see that the opposite also holds. So if there is a multi-commodity flow network defined by an integer set of variables, x and y, then if that has a feasible flow, then that will correspond to a feasible solution to the problem that we wanted to solve. So we can write an integer programming formulation like this. We want to minimize the sum of the opening cost and the connection cost. And the only constraint that we have is that the flow network we have just defined using x and y has to have a feasible flow. And of course, we will have to have the integrality constraint as well. But that is an exact formulation for the problem. Now, of course, solving this problem is NP hard, so we cannot solve it algorithmically, at least in polynomial time, probably. So we are going to relax the last integrality constraint a little bit, and we are going to say that instead of all these decision variables being either 0 or 1, it has to lie somewhere between 0 and 1. And that is the standard LP relaxation, written in a slightly more complicated way than usual. Yeah. Now, one of the questions that you could possibly ask is, why do we need this commodity specific capacity when there already is a commodity oblivious capacity? But then it is easy to see if you think about a very simple instance where there is only one client and only one facility, and that facility happens to have the capacity of 10. And then if we didn't have the commodity specific capacity, then the LP would look like as if we can just open that facility by a fraction of 1 over 10, and then it has enough capacity, therefore it will be able to accommodate the flow that is coming from the client. But if we have the commodity specific capacity as well, then the LP will imply that the opening variable of that facility also has to be at least 1. So that is the reason why we have this commodity specific capacity.
So is that going to be some lower bound on the flow from this client to? Or?
You mean in a feasible flow?
Yeah. So what's the meaning of yi.1? I'm trying to.
Oh, because, well, it will become a little more clear later, but see that each client is a source of flow of demand 1, and that 1 is coming here, basically. So, in other words, a facility that is fully open can only receive a full flow from each of the client, right? Because, well, if you think about the integer program formulation, then it's either 0 or 1, and is that an enough answer, or maybe? So, if a facility is open, then it should be able to receive a flow that is coming from a specific client. And of course, the minimum or the minimum capacity that we can safely specify for that facility would be 1, because there is only 1 unit of flow coming from a particular given client. That's why we say the opening variable times 1. On the other hand, if the facility is not open, then we have to say that no flow can come to here. Then again, the opening variable y sub I would be 0, therefore its commodity specific capacity will be 0. Okay. So in some sense, I didn't have to write the multiplication by 1. I just wrote it because it's later going to be changed slightly. Anything else? Okay, so let me first show you why the standard LP relaxation is too weak. So here what I mean by too weak is that when the gap, the multiplicative gap between the true optimum and the LP optimum can be arbitrarily large, and that is a bad sign because in the analysis of the algorithm, we would want to use the optimal solution to the LP as a lower bound on the true optimum, and then, well, if the lower bound is too bad, then we don't have much hope. So in this instance, the distance is all zero. If between any pair of nodes, the distance is zero, it's all about the opening cost. Now, this facility both of the facilities have capacity of 10, but there are 11 clients. This facility is free. This facility has an opening cost of 1. And then, obviously, the optimal solution will have to open both of the facilities and pay the cost of 1. Now, the LP can, of course, cheat by fully opening this facility and opening this facility by a fraction of 1 over 10, and then send 10 over 11 unit of the flow demand from each client to the first facility, and 1 over 11 fraction of the flow demand from each client to the second facility. And then we can easily verify that this is a feasible solution, but has a value of 1 over 10, and of course, this can be arbitrarily bad. So in order to strengthen this LP relaxation, because that's the first step that we need to do if we want to get a good approximation algorithm. So in order to do that, we are going to consider some arbitrary partial assignment or partial function that assigns some of the clients to some of the facilities. And then, well, basically the intuition is that we are going to treat it as if this is going to be part of our final solution. And then what we want to say is that the LP solution itself, even after doing this particular partial assignment, still has to be a feasible solution for the clients that remains unassigned by this partial function. But that, on the other hand, well, means that if we use a similar notation that we used to introduce the standard LP relaxation, we want to define a similar multi-commodity flow network and want to say that this network has to have a feasible solution, feasible flow. So, in this new multi-commodity flow network, only the remaining clients, the clients that was not assigned by this partial assignment, will be creating a unit flow. And the commodity oblivious capacity of each facility is now going to be the opening variable times not the original capacity, but the original capacity minus the number of the amount of its capacity that was already used by the partial assignment. And then we can see that this multi-commodity flow network, for example, has a feasible flow. These 4 clients generate a unit flow. Now I'm going to route the unit flow from this client to there, which has a commodity oblivious capacity of 2. And this facility has a commodity oblivious capacity of 3, so I can just route all the 3 units of flows to that facility. So this one actually has a feasible flow. So for those of you who are familiar with the knapsack cover inequalities, this type of constraint is in a similar spirit as these inequalities. Now the final LP that I would like to write will have a constraint that says for any possible partial assignment, the flow network that is defined by now not just the LP solution but also defined by the partial assignment has to be feasible. But then the question is this really still a relaxation? Didn't we rule out an integral true solution? Well, the answer unfortunately is no, because you can think about this partial assignment and you can see that, for example, now the commodity oblivious capacity of this facility has decreased all the way to 0, regardless what the opening variable is, because the capacity, we have already used up its capacity. But then the only, well, at least when you think about this particular LP solution, which is an integral solution, therefore shouldn't be ruled out, we can say that the only edge that is coming out of this client goes to this facility, which now has a zero capacity and therefore cannot accommodate any further flow. So this is infeasible. So in order to make this multi-commodity flow network feasible again, I'm going to introduce some edges that correspond to the partial assignment that is defining this multi-commodity flow network. So I'm going to introduce an arc from the facility to the clients according to the partial assignment. And now flows can be routed along this alternating path. And likewise for the other two clients as well. And we can see that this multi-commodity flow network is feasible again. So an alternative way of thinking of this backward edge is basically that these edges will provide a chance to undo some of the partial assignment if that partial assignment is not something good. So that will ensure that the multi-commodity flow network we have just defined will have a feasible flow. So here is our relaxation. So the relaxation is again just minimizing the solution cost, and the subject, the only type of constraint we have is that these multi-commodity flow network have to be feasible for any partial assignment G. And again, the multi-commodity flow network was defined by having a forward arc from client to facility, which has a capacity that is given by the connection variable, and a backward arc of capacity 1 if G assigns that client to that facility. And each client acts as a source of its own commodity with unit demand if it is not already assigned by the partial assignment. And each facility is a sink of flow, which has a commodity oblivious capacity given by the opening variable times the reduced capacity, and the commodity specific capacity, which is equal to the opening variable. So that's our relaxation. Any question?
So this throws in more constraint
Yes.
to the initial relaxation. Right?
Yes, in fact, quite a lot. Now let me show you how the previous example is now ruled out. So I'm going to think about the multi-commodity flow network defined by this particular assignment, partial assignment. I'm assigning these 10 clients to the first facility. So now whatever value I'm going to choose as the opening variable for this facility, its commodity oblivious capacity will be 0. Therefore, in order to accommodate the unit flow that this client is generating, I will have to open this facility with the opening variable of 1. So now I can see that there is a hope that this LP will actually have a constant integrality gap. So there are a couple of things that I would like to mention. This LP relaxation automatically embraces the standard LP because if you think about it, the way how I introduced the standard LP was exactly by describing a special case of this multi-commodity flow network corresponding to an empty partial assignment. And this also embraces the knapsack cover inequalities I have mentioned about for the min knapsack problem. Now, we don't know how to separate this LP. So we don't actually know whether the optimal solution to this LP can be found in polynomial time. But the LP rounding algorithm that we are going to show uses the feasibility of the multi-commodity flow network only for a single value of partial assignment. And what we do know is how to separate this LP for a given partial assignment. And then using the standard techniques, we can actually obtain a constant approximation algorithm for this problem. Let me elaborate a little more why it is possible. So, well, when you think about the usual ellipsoid method, they use an exact separation oracle. You either find the violated inequality or correctly decide that the current point is in the polytope. But now what you're going to give instead is a relaxed separation oracle, which either correctly finds a violated inequality, or without deciding whether the current point is in the polytope or not, it will just find an integral solution whose cost is within a certain factor compared to the current point. And our rounding algorithm actually gives such a relaxed separation oracle because our rounding algorithm does not directly rely on the optimality of the LP solution. And we can separate with respect to any given partial assignment. And then if you think about in particular, the optimization version of the usual ellipsoid method, then the way how it works is it queries the exact separation oracle with the current center of the ellipsoid. And then it will either find the violated inequality or determine that the current point is infeasible. And what the optimization version of the ellipsoid method will do is at that point just add another hyperplane that says from now on I'm only interested in the points that has a strictly worse cost compared to the current center of the ellipsoid. Now we can run this ellipsoid method exactly using the relaxed separation oracle. So it either finds an inequality that is violated by the current center point, or it will round the current center of the ellipsoid. And then this is a candidate solution that I may at the end of the algorithm produce as the output. But in that case, I will just add the constraint that says from now on I'm only interested in the solution that has a better cost compared to the current center of the ellipsoid method, and then continue. Okay, so as I promised, the proof is going to be algorithmic. So let me show how we can actually round the fractional solution to this LP into an integral solution. So the first step of the algorithm is something quite natural, I think, which is partition the entire set of facilities into two sets. So I, standing for nearly integral, these facilities has an opening variable that is quite high, let's say strictly greater than 1/2. And S, representing small, has a small opening variable. They have an opening variable that is smaller or equal to 1/2. And we just open all the facilities in I, because LP has paid at least half of their opening cost, so we can afford it. And then we are going to choose carefully. I will describe what carefully means later. But we choose a partial assignment carefully that assigns some of the clients to the facilities that we have opened at this point. And then that's exactly going to be a part of our final solution. We are going to assign every client that is assigned by this carefully chosen partial assignment exactly to that facility that the partial assignment is assigning that client to. So here I'm writing our wish list lemma. So the first thing that I wish is that I want this partial assignment to be cheap, because I'm going to include it as a part of our final solution, so it better be cheap. And then after assigning the clients that are assigned by the partial assignment, I will have to produce a complete solution. Therefore, I will have to assign the remaining clients somehow to some facilities. And in order to do that, I'm only going to use the facilities that is in S, that has small opening facility. So of course, one of the challenges will be to make sure that I'm not spending too much on the opening cost, because at this point, I cannot automatically say that the LP has already paid enough to open some of these small opening facilities. And then, as it turns out, there is a corresponding item for the last step to be successful in our wish list lemma, which is the multi-commodity flow network we have just described. And for the carefully chosen partial assignment G, has a feasible flow where all the flow is going to be drained at the facilities that has small opening. So that is the second item of our wish list lemma. Now let me show you why this is the right thing to pray for. So remember that this is all about the last step of the algorithm, where we assign the remaining clients to the facilities that has small opening. Now, one thing I would like to observe is that the multi-commodity flow network, even when we restrict ourselves to the facilities with small opening, it will still be feasible, because all the flow are going to be drained at the capacities with small opening. So we can, in some sense, ignore the facilities that has a large opening or the nearly integral facilities, because these are not going to matter. These are not going to serve as a sink of a flow. So we can omit that from the instance, sort of. And then one additional argument is that now we do the same thing for the clients, because some of the clients are not generating any flow. Only the clients that was not assigned by the partial assignment is generating a unit flow. So we are going to omit these clients that is already assigned by the partial assignment also from the instance. And then this still is this multi-commodity flow network still is feasible. But now we can say that our partial assignment is the empty assignment, because we have already removed all these clients that is already assigned by the partial assignment. And then what I would like to point out is that this exactly is the standard LP relaxation. And then one more thing that I would like to mention is that the commodity oblivious capacity of every facility with small opening is bounded away from the true capacity of that facility, because the opening variable is strictly smaller than 1/2. Therefore, the commodity oblivious capacity of that facility in the multi-commodity flow network is also at most 1/2 of the true capacity of this facility. So in other words, the capacity constraints for these facilities are not tight. Now, one thing I mentioned in the previous slide is that even though standard LP does not give any reasonable bound for our problem, it does give a good bound for many of the relaxed problems. And one of the relaxed problems was that the capacitated facility location problem, where some of the capacities are allowed to be violated, but as long as it's violated by some provable factor. And in particular, Abrams et al. Gave an approximation algorithm that gives an 18 approximation solution where the capacities can be violated by a factor of 2. But we don't care about this because the capacity constraints are not tight. They are already at least factor of 1/2 away from the true capacity. So we can simply apply their algorithm using the solution to the standard LP relaxation, and then that will deal with the final step where we assign remaining clients to the facilities with small opening. And that's the reason why this is the right item that we want to have in our wish list lemma. Any question? Okay. Now, of course, what we want to prove usually is not true. But what we can actually prove is we can choose a fractional partial assignment, not an integral partial assignment. And then, even though not all the flow is going to be drained at the facilities with small opening, we can say that at least half of each commodity will be drained at the facilities with small opening. That's what we will be actually able to prove. And then by using that 18 approximation algorithm, we can show that this gives a 288 approximation algorithm based on a linear program relaxation. And there are some obvious improvements, but probably not leading to 5. And of course, 5 is coming from the local search approximation factor. And in fact, determining the exact integrality gap of this LP remains open, and I think is one of the interesting open questions. But let's go back to the first ideal version of the wishlist lemma, and I will show you why this lemma is true under some simplifying assumption. So the simplifying assumption is that we're going to think about the support graph of the LP solution, or in other words, the set of edges on which the connection variable is non-zero. And then the assumption is that for each client, all instant edges have the same cost. Or so in other words, what that means is that, well, whichever edge we choose in order to partially assign this client, it doesn't matter because they all have the same cost, therefore LP has already paid for it. That's the simplifying assumption. Of course, this is not generally going to be true. Now, under this simplifying assumption, again, let me remind you that the first step of the algorithm was to divide the partition, the set of facilities, into nearly integral facilities and the small opening facilities. And then we had opened the nearly integral facilities, and the following step of the algorithm was our only chance where we could use of these nearly integral facilities, right? Because the final step of the algorithm was purely relying on the facilities with small opening. So what sort of makes sense is that given that this is our only chance where we can use the facilities that is nearly integral, probably we want to make the best use out of it. So that's why we want to find the maximum matching. So we want to find the maximum bipartite matching G on the support graph, where each client can participate at most once, because we only want to assign it somewhere. And each nearly integral facility can match or can be assigned up to the clients as many as its capacity. And of course, every facility that has a small opening variable is not open yet, so we don't want them to participate in the matching. So let's say that this is the maximum bipartite matching. I know that this is not the maximum bipartite matching, but bear with me for the moment. And then now we observe the multi-commodity flow network that is defined by the LP solution X, Y, and the partial assignment that we have just chosen, G. And then what I claim is that there cannot be a path from a remaining client, or in other words, a client that does generate a unit flow, to a facility that is not fully matched by the bipartite matching. So what I claim, in other words, means that there cannot be such a path. This client is generating a flow, and this facility is not fully matched by the bipartite matching. So there cannot be a path, but there actually is a path, and the reason is because I didn't choose the maximum bipartite matching. And the proof is exactly what this picture is showing. If there is such a path, then the corresponding path in the bipartite graph will be an augmenting path, and that's the reason why if we have chosen the maximum bipartite matching, there cannot be such a path. But then remember that a facility that is fully matched by the bipartite matching has a zero commodity oblivious capacity, so they cannot be draining any flow. So, in other words, there cannot be a path from a client that is generating a flow to a facility that has non-zero commodity oblivious capacity but is in I. Therefore, all the flow from these clients has to go to the facilities with small opening. And that's how we prove the second item of our wish list lemma. So of course now I will talk how we can lift that assumption, and without the simplifying assumption, how we can prove the real version of the wish list lemma. So the problem is that the partial assignment we find in that way can be quite expensive compared to the LP solution, because what the simplifying assumption had given to us was exactly, regardless which edge we choose from the set of edges that is incident to a given client, it didn't matter, because we assume that all these edges have the same cost. But that's not true, and that's where exactly the proof gets broken. And the solution is we are going to find the fractional partial assignment whose cost we can charge against the LP solution. So in particular, that means I'm going to find the set of values G such that every client is fractionally assigned up to once, and every facility is fractionally assigned up to its capacity if the facility is a nearly integral facility. And I don't want the facilities that has small opening variable to participate in the matching. And of course, we all know that this can be found by solving the maximum flow. And the reason why I'm showing this graph is because I'm going to talk about the augmenting paths in the flow network. So this can be slightly confusing, but I'm talking about a single commodity flow network that is used to find the maximum matching from the bipartite graph. And I will be also talking about the multi-commodity flow network that we have been talking all the time so far. Now, one problem is that, okay, it's good that we find the fractional partial assignment, but the definition of the multi-commodity flow network was only talking about the near integral version of the partial assignment. So I will extend our relaxation, and extending is within parentheses because I'm actually not doing anything, because these two relaxations are exactly the same because of the integrality of matching. But so I'm going to say that the multi-commutative flow network has to be feasible for all fractional partial assignment, and I slightly changed the multi-commutative flow network's definition. So instead of saying that the backward edge has capacity 1 if the client is assigned to that facility, now I'm saying that it has capacity that is exactly equal to the corresponding partial assignment, of course. Now, instead of saying that each client generates a unit flow if it's not assigned, it generates a flow whose demand is exactly equal to the amount by which the client is not assigned. And every facility is a sink of commodity oblivious capacity given by the fractional version of the reduced capacity. And now this is why I wrote 1. Instead of saying 1, I can say the opening variable times the demand of that client. Okay? So that is the fractional version of our relaxation. And again, this is exactly the same as the integral version. So this was our wish list lemma. So I have actually replaced the first constraint, which said G is cheap, with the particular version that we were able to show under the simplifying assumption. But the problem is that this is too good to be true. Because if you think about this particular, somewhat stupid but still feasible LP solution, there is one client and two facilities, each of which is opened by a fraction of 0.99 and 0.01. And then, well, even though I'm showing a particular case where the partial assignment is assigning this client to that facility as much as allowed by the bipartite graph, but regardless how large the partial assignment amount is, the commodity specific capacity of this facility is always going to be given by the opening variable 0.01 times the demand of this client. So, and remember that this is the only facility that is in the set S, the facility that has small opening. So only 1% of the entire demand of this client is going to be drained at the facility with small opening. So what we hoped for in the second item definitely is not true. So my solution is to introduce 2 here. So it's not bounded by the LP solution, it's bounded by twice the LP solution. And now you can see why I have in particular chosen 1/2 here. That's the reason. So, but let me step back a little bit and think about what is sort of the final goal of our entire analysis. And even though it may sound slightly strange if you first hear about it, but our goal is not really in making the multi-commodity flow network feasible, because that's something the ellipsoid method will take care of. Our goal here is actually trying to make the multi-commodity flow network infeasible unless it's going to be able to generate a flow that has all these nice properties. So I'm actually going to make it harder. So in other words, I want to find a partial assignment that leaves on some of the clients too much demand in order for that demand to be served only by the capacities that remains in the nearly integral facility. So in other words, they will have to go to the facilities with small opening. Now, let me remind you that there were 2 different types of paths in the argument that I showed under the simplifying assumption. In the multi-commodity flow network and in the residual graph that was used to find the maximum bipartite matchings. So these 2 paths. So the previous argument written in a single sentence was that a path from a client with positive demand in the multi-commodity flow network to a facility in I with positive capacity corresponds to a path from an undermatched client in the bipartite graph to an undermatched facility, and therefore it cannot exist if we have chosen a maximum bipartite matching. That was the argument. But that sentence does not hold in the fractional version, and here is an example. So I have, all the weights have got weight, all the edges have weight of 1/2 in these examples. So this is part of a fractional solution because I have omitted the facilities with small opening. Now this is a partial assignment where this client is fully assigned, split into 2 facilities, and this client is assigned to only 1 facility by a fraction of 1/2. And this will be the corresponding residual graph in the bipartite graph. And now I can see that the multi-commodity flow network actually has the path that starts from this client and goes there, and gets here. But the residual graph does not have a corresponding path. So the same argument cannot be used here. But I will do something very similar. So I'm going to consider a maximum fractional matching G and the residual graph in the single commodity flow network that was used to find the maximum matching. And now I'm going to partition the set of clients and set of facilities into a few sets. So everything with subscript R is the set of vertices that are reachable from an undermatched client in the residual graph. Subscript N is the other vertices. So some of the clients are reachable from an undermatched client, some of them are not. And I have also applied the same criteria for the nearly integral open facilities, and small facilities are small. And now I'm going to consider the multi-commodity flow network that is corresponding to that case, and I will observe what happens in 2 of these graphs. Now, first easy observation is that none of the facilities in I sub R, which is a set of facilities that is reachable from an undermatched client, can be undermatched, because that means we can augment that bipartite matching. So in other words, I sub R all have 0 commodity oblivious capacity, and that's the reason why the only potential point where the sink of the multi-commodity flow network can lie are I sub N and S. On the other hand, every client that has positive demand is in D sub R because, well, a client is reachable from itself. So again, in the multi-commodity flow network, this is the only place where flow can be generated, and this is the only place where flow can be drained. Now consider a client that is in D sub R and a facility in I sub N. And what I can see is that this particular edge in the single commodity flow network has to be saturated, because otherwise there would have been an edge from this client to that facility in the residual graph. Therefore, this facility would have been reachable. And because that's not the case, what that means is that, well, this edge is saturated, and in other words, the maximum bipartite matching G, Ij, is exactly twice the LP solution. Oops, I didn't mention that when I'm defining the... Oh, I did mention, actually. I just didn't say it, but when I showed the formulation, the edge capacities were set as twice the LP solution, and that's the reason why in our wishlist lemma we can make sure that the partial assignment we choose is within a factor of 2 compared to the LP solution. And then this is where I do the slightly counterintuitive thing. I actually set the corresponding values of the partial assignment to be 0. And then that will increase the demand of that client by the total amount of, or the total capacity of the edges from that client to all the facilities in I sub N times 2. Right? Because I'm undoing some of the partial assignments, and that will exactly reflect it to the demand of that client by an increase in its demand. And remember that all these edges were saturated, so I'm increased by undoing the partial assignment from this client to that facility. For example, I'm increasing its demand by twice the LP solution value between these 2 vertices. And once I do that, what I can say is that for every client that may be a source of the flow, its demand has to be at least twice the total capacity of the arcs from that client to all the facilities, all the nearly integral facilities that may act as a sink of a flow. And that holds for every client. And compare it to the previous statement where I previously said under the simplifying assumption, there just simply cannot be a path from each of the client in D sub R to any of the facilities in I sub N. So I have obtained something analogous. Well, it's not really completely the same, but what I'm basically saying here is that for every client that can be generating some flow, if I think about all the capacities that goes to the undesirable place where flow can be drained, its capacity is at most 1/2 of the demand of that commodity. And that's the reason why I can, well, using some surgical argument, I can show that at least half of the flow has to go to the facilities with small opening. So that was a proof by a lot of hand waving and picture. But that will actually show that we do have a good LP, and its integrality gap is a constant, and this is a polynomial time constant approximation algorithm based on LP. So we have answered the question whether we can obtain an LP-based technique to solve the capacitated facilitation problem. And then that gives rise to a number of follow-up questions, such as, well, one of the reasons why, so there was a slide where I was talking about why we are interested in this question, why we want to find an LP-based approximation algorithm for the capacitated facilitation. And these questions exactly correspond to those items. So the first reason why we wanted an LP-based approximation algorithm was because we wanted to get an access to the rich toolbox of algorithmic techniques that already has proven to be highly successful in the uncapacitated case. So we can ask exactly the question, whether, given that we do now have a strong LP, if we can use those techniques to, in conjunction with the new relaxation, to obtain better approximation algorithms. Another question is if we can apply any of these techniques to the similar problems that share similar LP relaxation, and also if we can improve the integrality gap bounds, as I have mentioned. So that's it for today. Thank you.
Thank you. Any questions?